Okay, tonight we're going to talk about velocity, just the different types of velocity. Now remember guys, there's three basic types, and we're going to talk about the three of those today. We're going to talk about what is average velocity, what is constant velocity, and what is acceleration, or uniform acceleration, which is basically a constant change in velocity. Okay, so let's say that we in fact have. First off, let's see what this graph means. Now, you might notice, you may think that this is an XY scatter. I'm going to treat it a little differently tonight. I'm going to treat it like it's a vertical bar graph. Now, this right here, this represents that for the first second, from time 0 to time 1, for the first second, our object has traveled 1 meter per second. So this would be 0, this would be an object not moving, and this would be maybe like 3 meters per second. Okay. So objects travel, right? And they can travel any velocity they would like, but then sometimes they change velocity. And we might see something like this. So you may be saying to yourself, Mr. Shaw, what the hell is this crazy stuff? Well, let's take a look at what I'm actually trying to demonstrate here. Okay. So we have this profile of an object's velocity, and we'll see here from 0 to 2, from 0 to 2 in our time scale. Actually, from 0 to 3, we're traveling at a constant velocity of 2 meters per second. But then you'll notice once we get to 3 seconds, we start going 3 meters per second until we get to 9 seconds. And then we slow down. We're traveling 1 meter per second. And then at 10 seconds, we're going 2 meters per second again. And then we're back up to 3, and then back down to 2, and then back up to 3. And you may say, well, obviously, Mr. Shaw, this is not constant velocity. This is not. We have a sporadic, a very dynamic, changing velocity. So the first one we're going to try to do is we're going to try to find our average velocity. So, and we can easily start off by doing this by just taking the average of any values. And when you take the average, that's basically the total number of values. We'll use the sigma total values divided by our number of values. So I'm going to add up all these blocks and then divide by the numbers. So you'll see here, guys, we have 6 blocks here. I have 3, 1, 2, 3, 1, 2, 3. I'm sorry. 1, 2, 3. 1, 2, 3, 4, 5, 6. So I have 3 times 6. I have 18 blocks there. I have 1 block here. I have 8 blocks here. I've got 6 blocks here, 4 blocks here, 6 blocks here. So let's add these up. 10, 14, 19, I messed it up, 25, 24, and you'll see that when I add 25 and 24, I should get 49. And that would be all my velocities added up for each of these seconds. And how many seconds did I go for? I went for 20 seconds. And that will give me my average velocity in this case. Now in my class, we usually deal with this. We usually go displacement divided by time. Now, one thing to notice, and we'll see something in a second, where average velocity and constant velocity, they have a close relationship. So right here, guys, this is how, if you could have the power to count the velocity of an object for every second and simplify it, you could calculate the average velocity that way. We're not really going to do this in this class, but I hope this sheds some insight into what is average velocity. It's basically if you had a velocity over a period of time, if you could count up the number of seconds and find the velocity at each moment and then divide that out, you could find the average velocity. In this case, it's going to be something around 2.5. Okay, now let's take a look at constant velocity, and that's a time when velocity is just simply not changing. So I'm going to make my row first and foremost like this. And I'm filling all these in. There should be some easier ways of doing this. I have an idea. I'm just making some holes in this, and we'll see what's going to happen in a second. So when I just come over here and do this one click, Click. There we go. So I filled this in. Ignore the holes I've made. And that's just, I've made those holes so it filled in quicker. Now, this is an object. We're going to leave it as is right now. And this is an object you'll see that has a velocity that does not change. Look, it keeps at 5 for the entire time we're here. Now, if you wanted to count these up again, you'd go 5, 5, 5, 5, 5, 5, 5, 5, 5, 5, 5, 5, 5, all the way out to 20. You would have 25s. Okay? And 20 times 5, and you guys should be able to do this, is 100. 20 times 5. And then how many seconds do you have? 20 again. And you will find out that you have an average velocity of 5 meters per second. So guys, this is the interesting case, and this is where a lot of students get confused. They think when they see this right here, this can also be simply, it's oftentimes written as V equals d over t. Now the thing I must stress is that this v is your constant velocity, and this formula only works when you are traveling at a constant velocity. Now you may be wanting to say, well, Mr. Shaw, how do I know if I'm not traveling at a constant velocity? You'll have acceleration. If you have a change in your velocity, if your velocity changes anywhere, imagine you have this, if you just have that right there. Now you no longer have a constant velocity. You cannot use that formula. You can only use this formula when it's like this. If it's this or this, you cannot use the velocity, the constant velocity formula. You'll have to use the some kind of acceleration formula or count them up. Now in this class we're really not going to come across this. This would be non-uniform acceleration. Let's take a look at what uniform acceleration is going to look like. Uniform acceleration, the easiest thing to see is going to be like this. Actually, let me do my cheat. Let's poke some holes in these so that I can be quick about it. Alright, just poking some holes so that when I use the paint can, it will fill everything up. And hopefully it works out well, because if I make a mistake, it's going to be a pain to fix. Alright, let's play it safe. This is not working out like I thought. Oh, maybe it is. I'm just going to stop right there for a second and see what happens. Okay, not bad. Not bad. So I'm just going to go... Oh, no, that's wrong. Okay, so here is an example of what uniform acceleration would look like. Now, you may say this can obviously be a line, like if I started here and went to here, this would obviously be a line. And that is true. That is true. And that line would actually represent, maybe I can draw better, Control C. Let's see if I can draw better. Go right here. There we go. That's a good looking line. So that line might actually represent our constant velocity or something, but this is a very simplified idea, guys. And let's just count them up like we have before so that we can see what the velocity, the average velocity here is. And it's not going to relate to the acceleration. So here we'd have 2. That's not what I want. Here we would have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So we'd add all these up. You'd get 6, 14, 22, 30, and 38. And then we could add these up again. This is how I just do it. So we get 20. And then we'd get 52, and then we'd get, adding this one together, you would get 90, 110. A little bigger than what I thought, but if you divide that by 20, what you'll end up seeing is that you actually get 55, I think it is, or 5.5, 5.5, maybe. I don't know, I don't have a calculator with me. Don't hold me to that. So, this is an example of what uniform acceleration would look like. Now, a lot of times people are like, well, how does some of the other big concepts relate to that? So let's see what some of the other big concepts are. If you look right here, here we are at time 0. That velocity at time 0 is your VI. And then what we do is also look over here at our very end, our last time, time 20. Maybe we'd say that's the end of our experiment. That would be our VF, and it would be 20. Okay? So I hope that makes some sense. It'd be equal to, that'd be meters per second, but don't be mad at me. It's a little rough tonight. Some things I really want to stress, guys, is that VF, that can be any point. When you're doing calculations for VF, you can calculate this as your VF, or you can calculate that as your VF. As long as it's not this, you can use the VF formula to solve for it. Okay? Please let me know if you have any questions over this. Hopefully this is illuminated to some extent what the difference is. This is once again an example of non-uniform velocity, non-uniform acceleration, but we could find the average velocity. Here, when we had this like this, this is this right here would be constant velocity, and here we have uniform acceleration. Okay, that's the big stuff we need to understand for this class. Okay, talk to you later.